Hello, my name is Gaurav Pawar, and I'm a PhD candidate at New Mexico State University. The paper I'll be presenting today is titled APECS, a Distributed Access Control Framework for Pervasive Edge Computing Services. This work was a collaborative effort between my colleagues at St. Louis University, New Mexico State University, and Intel Labs, and is part of a project funded by Intel Labs and the National Science Foundation. Before we begin, here is the outline of the presentation. I will begin by briefly introducing the concept of edge computing and the emerging field of pervasive edge computing environments. Then I will go over the proposed solution APECS and its components. Finally, I will discuss our analysis of APECS along with the experimental results before concluding the presentation. The increase in demand and volume for latency-sensitive applications like image processing for vehicular networks and video analytics for certain IoT devices like cameras has led to the idea of moving computational resources closer to the network edge. This is in contrast to how such resources are traditionally located in data centers, in key locations, and generally further away from end-user devices. Various kinds of edge ecosystems like cloudlets and fog computing systems have been proposed in the literature to address these needs. Some of the benefits of edge computing systems are low latency, request aggregation, and privacy. Low latency is required, for example, in the autonomous driving application scenario, where the computation result is time sensitive. Request aggregation in edge computing systems reduces upstream bandwidth when large number of user devices in a certain geographic region are requesting similar data. Edge computing systems provide for better privacy because the computational services are located closer to the end user devices. So the user data stays localized to the edge, and this reduces the number of devices that the data traverses. Recently, the notion of pervasive edge computing architectures has emerged that suggests the inclusion of user-owned devices into the existing edge platforms. This creates a larger pool of heterogeneous computing resources and helps in democratization of the edge. A pervasive edge computing ecosystem aims to utilize all available computational resources at the edge, including all idle peer devices, for example, smartphones, tablets, laptops, and vehicles, to assist with edge computation requests. This opens up various opportunities for improvement, for example, privacy, reliability, and trustworthiness. One of the most important challenges of PEC is the multi-stakeholder nature, where multiple trust domains are involved in performing a requested service, thus making it challenging in trusting all the entities involved. The multi-stakeholder environment of PEC leads to dynamic member pools and device heterogeneity as user devices in the edge become available for service execution from time to time and also leave the environment when they are not idle. Due to the dynamic nature of the environment, traditional service discovery mechanisms are not feasible in PEC. This leads to problems setting up TLS connections to edge resources since they require discovery. Traditional cloud-based access control schemes need an always-on authentication server and hence cannot facilitate asynchronous requests in the PEC environment. We designed APECS as a hybrid approach to edge access control that removes the weaknesses inherent in single source of trust access control designs. APECS uses multi-authority attribute-based encryption, MAB in short, for access control of edge devices, which we will detail in later slides. Now I will introduce the different entities in our framework. First, there are service providers. These are entities that provide software or services which the end users are interested in running. These service providers often deploy their resources in the cloud in partnership with cloud providers for better scalability and performance. There also exist base stations, which are local to a given geographic area. These base stations are owned and operated by communication and internet service providers like AT&T and Verizon. These base stations themselves could also provide computation services and act as edge nodes. All edge devices in a given geographic region communicate through the base station of that region whenever they communicate with all other devices in the region or to the cloud. These edge devices, as mentioned before, are user devices that are willing to join the PEC environment and run services on behalf of service providers for the users of the PEC environment. For example, a vehicle with enough computational resources could run a Snapchat VR application for a user in the PEC environment connected to the same base station as the vehicle. In APECS, each service provider runs an attribute issuing authority, which is part of the MABE system in the cloud infrastructure. Each base station is in the PEC environment also runs an AIA, which is part of the same MABE system. All edge devices in the PEC environment receive attributes from the service providers according to the services they wish to provide, and attributes from the base station that they're associated with. Resource consumers and end user devices periodically obtain tokens from service providers according to the computation services they wish to avail from the PEC environment. In APECS, the user submits the service request, which is forwarded to the relevant edge servers by the base station. Upon successful computation, the base station relays the edge server's response to the end user. We note that APECS supports two kinds of services, static services and dynamic services. Static services are requests for multimedia data and web content, and dynamic services are services that require unique user data like image annotation and video analytics. We note that in APECS, the service provider and base stations are trusted, relaxing this assumption as ongoing work. We also trust edge servers to perform computation correctly. If one is worried, this assumption can be addressed by adopting verifiable computation techniques. The first attacker is an unauthorized user whose goal is to access the edge resources through forged, shared, expired, or even without using any credentials. The adversary could also mount a spoofing attack by impersonating an authorized edge server to hijack or obtain user data. Lastly, an adversary could be some authorized edge server, which colludes with an unauthorized user to provide it with computation services. First, let's look at the steps involved in APECS when users request static services. As mentioned before, these services do not require any user-specific data. So in this case, first a user signs up with a service provider for a service and is issued an access token. This token is included by the user in all service requests for a given service provider to the edge servers. The edge servers verify the access token before processing a given user request. The response data from the user request is sent from the edge server to the base station that relays it forward to the user. We note that in the edge servers and the users do not need to talk in real time in APECS. Now let's look at the structure of the access tokens in APECS. APECS uses a unique token structure based on the Java Web Token, which is superior to traditional OAuth tokens that can be borrowed like bearer tokens. The service provider signs the token whenever it is issued, and the user also signs the token when accessing services. Here, LU indicates a list of authorization levels for a given user like bronze, silver, etc., to be matched against a required authorization level for a service at the edge server. The token also includes a list IDs of S, which could be a list of services which require explicit permission and might not be covered under authorization levels listed under LU. APECS trusts the service provider to provide well-formed and correct tokens for the requested service category, and each user gets a unique token from every service provider he or she is subscribed. While tokens are used to authorize users in both static and dynamic requests, dynamic services require authorized servers to access user data. In this case, MABE scheme is used to ensure authorized access on the part of the edge servers. The MABE scheme has 4 algorithms. The setup algorithm generates public-private key pairs for all AIAs, among other things. The keygen is run by an AIA and is meant to generate an MABE user's attributes and secret keys associated with the attributes, which in this case would be for the edge servers corresponding to the services they're going to provide in the PEC environment. The encryption algorithm can be run by anyone with access to the public parameters and encrypts a message with an attribute set such that only someone whose keys have enough overlap that is given above a threshold with the attribute set can decrypt the given ciphertext. The decryption algorithm helps someone with the threshold set of attributes as defined during message encryption to decrypt the ciphertext. Now let's look at the steps involved in APECS when users request dynamic services. In the first couple of steps, the edge server contacts the service provider to tell it what services the edge server plans to provide and gets its relevant ABE keys. This is a one-time step that is done during setup. The edge server also contacts the base station and gets attributes from the base station when it registers to provide services in the PEC environment. For example, in this case, an edge server connected to a Verizon base station 10 in LA receives attribute LAVZBS10 and also signs up with Instagram as a service provider to provide Instagram image annotation service, hence receiving Insta and Insta-Anno attributes. In the next step, a user encrypts a service request and user data, because this is a dynamic request, with a symmetric key. The given symmetric key is then encrypted using MABE with attributes relevant to the service the user is requesting. For example, a user connected to the illustrated PEC environment connected to the LA Verizon base station 10 and requesting an Instagram annotation service could have a message encryption policy as with attributes LAVZBS10 and Insta-Anno. The user's request, which was encrypted with the symmetric key, also includes her service token, which would prove that she is signed up for the Instagram image annotation service. Only edge servers with all 3 attributes will be able to decrypt the given user data and process the request. Upon successful token verification, the edge server computes the result, encrypts it using the included symmetric key, and the result is sent back to the user through the base station. We note that APECS does not require both edge server and clients to be online during the entire operation, and the user is free to move to a different PEC network and is still able to receive the service response. In case of malicious edge servers, requiring the cloud server to perform edge server revocation might induce latency and also introduces scalability concerns, where thousands of edge servers registered with a service provider AIA would need to be rekeyed. APECS introduces localized revocation. Whenever an edge server needs to be revoked, the base station revokes its attributes. This ensures that the revoked edge server does not possess the minimum threshold attributes required to access user data, and the rekeying operation is localized to the relatively small number of edge servers connected to the given base station. We prove APECS secure using universal composability framework. We refer you to the paper for the proof of this theorem and its associated machinery, including the ideal functionalities and their discussion. We also propose a modification to the APECS scheme, APECS PKC, which uses traditional TLS and service discovery in place of the attribute-based encryption scheme of APECS. This scheme is suitable for an approach where the edge server and the PEC client can interact with each other directly for the whole duration of the operation. We alleviate this need in APECS because authorization is done asynchronously. In APECS PKC, the user first performs a service discovery with the local base station for the available services. Then it establishes a TLS connection with the relevant edge server. In this scheme, in addition to users, edge servers are also issued tokens by the service providers, which are verified by the users before sending their service request data to the edge servers. Now we move on to the experimental results of APECS. We use the given devices for benchmarking the MABE operations of APECS and to emulate the different edge devices expected in a PEC environment, such as user devices, like smartphones, laptops, and compact PEC servers. First, we want to show how much time it takes to perform MABE encryption and decryption operations on the three aforementioned devices. The latency we observed is comparable to the delay incurred in digital signatures. A total of 6 attributes from 3 AIAs were used for the encryption and decryption operations, where 2 attributes were issued from each AIA. We implemented APECS PKC, APECS PKC and cloud in the form of 4 engines: a user engine, an edge engine, provider engine, and a cloud engine. All 4 entities were deployed on the Genie network with the layout as illustrated. The user devices and edge servers were deployed geographically closer to each other at the University of Colorado, and the provider and cloud server were deployed further away to simulate the network latency incurred in real-world networks. The provider server was deployed at Cornell University, and the cloud server was deployed at New York University. We measured the end-to-end latency of APECS, APECS PKC, and the cloud schemes for 1,000 service requests, while timing the individual components that make up the complete interaction between the entities. In APECS, the requests went from user devices to the edge servers, and the results were returned back to the user asynchronously. In APECS PKC, the user performed a service discovery first before establishing a TLS connection with the edge server for the requested service operation. Lastly, in the case of cloud computation, the user created a TLS connection directly with the cloud device for the requested service, and the TLS connection is terminated when the cloud is finished with the service computation, and the result is returned to the user. The gray part in APECS PKC and cloud, which indicates the network latency, includes the TLS connection associated cost for those schemes. APECS PKC incurs the edge token verification and service discovery cost, which is avoided in APECS due to attribute-based encryption. Here we show the average cost in milliseconds for each of the operations within the schemes for comparison. Cloud is trusted, so a user just creates a TLS connection to the cloud and is authorized by the cloud by verifying the user token. As mentioned earlier, MABE in APECS removes the need for edge token verification. We note that despite costly MABE operations, APECS outperformed APECS PKC in terms of authentication and authorization throughput. Here we compare performance of APECS and APECS PKC in terms of throughput. So in these graphs, higher is better. In APECS, for static services, only user token verification is required, but for dynamic services, multi-ABE operations are needed. That is the reason why we see a lower throughput for dynamic requests than static requests in APECS. Finally, to conclude, we presented APECS, which allows for synchronous authentication and authorization operations in the PEC environment. We also demonstrated the need to design tailored solutions that meet the needs of edge applications instead of retrofitting cloud-based solutions like traditional access control mechanisms. Thank you.